Okay, let's talk a little bit about the autoionization of water. Pure water will ionize ever so slightly, even though we usually consider it a covalent compound. The concentration of the ionized water is less than 1/1,000,000th molar at room temperature. It varies slightly with temperature. We can write the autoionization of water as a dissociation reaction similar to those we've previously done. We can imagine two waters reacting together to form a hydronium and a hydroxide. Because the activity of water is 1 and we don't include those in equilibrium constant expressions, we can write a Kw for our reaction, where Kw is equal to the hydronium ion times the hydroxide ion concentrations. The water that would appear in the denominator, since the reactant side does not appear because its activity is 1. Experimental measurements indicate that the concentration of hydronium ion and hydroxide ion at water at 25 degrees Celsius is 1.0 times 10 to the negative 7th molar. And that will vary with temperature. So Kw is equal to hydronium times hydroxide, or 1 times 10 to the negative 7th times 1 times 10 to the negative 7th. And so you get 1.0 times 10 to the negative 14th. You need to know that that's considered the ionization constant for water, or the Kw. And we'll use that in a number of calculations. And so let's look at that. And so let's say we take 0.05 molar HCl. We want to calculate the concentrations of the hydronium and hydroxide ions present in solution. We'll have to use our friend the Kw. So if we got HCl ionizing to form H plus, Cl minus, or if you want to throw the hydronium in there. But the point is that if this is 0.050 molar, after it ionizes, we know that if it completely ionizes, like we've done in previous videos, this concentration is 0.050 molar in aqueous solution, because HCl is a strong acid. And so we know our H plus then would be equal to our hydronium ion, which is 0.050 molar. Now what about hydroxide? We have to use hydronium times hydroxide equals our Kw, which we said was 1.0 times 10 to the negative 14th power. Where'd that come from? Just what we were saying, the ionization of the water in aqueous solution, and we just talked about that constant. So now I need to solve for the hydroxide ion. So hydroxide ion is equal to Kw divided by hydronium ion, where we got 1.0 times 10 to the negative 14th divided by 0.050. Technically, this would have units of molarity squared, and that would be molarity, so the units do work out. And so we're going to run that through our calculator. 1.0 times 10 to the negative 14th divided by 0.050. And we're going to get a hydroxide ion concentration of 2.0 times 10 to the negative 13th molar. Notice as the acid concentration gets large, the hydroxide ion gets small, and vice versa.